Hello, everyone, and thanks for joining me here. This lovely sunny weather today. Nice that you want to spend a little bit of time inside together with me for the next hour talking about WebAssembly components. My name is Mikkel, and I work for a company called Fermion. Fermion has been doing stuff with WebAssembly over the last soon-to-be 3 years. I've been part of the company for more than 2 years now, and what I do is I take care of developer relationships and products within that company. Fermion has a history from it's an engineering team. The core of the company is an engineering team that has history way back, but soon, the latest was being an open source engineering team within inside of Microsoft, which is where I got to know the team while also working there. Did a lot of stuff around Kubernetes, did a lot of stuff around Azure Kubernetes services and other types of services in Azure. The engineering team has founded projects like Helm and Draft and those type of things. So if you know about the Kubernetes world, some of those things would probably be known to you. But we, at Fermion, we are working on what we believe is the next technology, core technology that will power not just cloud computing, but all compute. Why set expectations lower than anything but that? And we believe that that is WebAssembly. So we think about this as sort of the next wave beyond what we learned from going from physical machines to virtual machines to containers. Consider WebAssembly to be a core technology for how we will build, operate, deploy, and all those things with the workloads, the applications that we create going forward. So with that being said, let's get on to this. We're trying to keep this as an introduction level, so I will gradually build things up, try to explain some of the core concepts behind both WebAssembly and the component model, but also dive into code, and we'll see some samples. And I'll see if we can get to have Q&A at the end. There's a microphone here. If not, I'll stick around, and I'll be happy to have conversations with all of you. Okay. So what really is the problem that we're trying to solve here, and the goal around WebAssembly? Well, originally WebAssembly was a specification invented to expand programming language support for the web. And when they talk about the web, they really mean the browser in this case. So this is kind of a response to what people learned from having things like Flash and Silverlight and Java applets, like a lot of proprietary standards to extend experiences building inside of the web. So being able to build these safe, portable things that are fast because they execute efficiently and that are compact because they are small is really what the WebAssembly specification is about. So WebAssembly coming out of, having a way of bringing new programming languages into the browser. There are some design principles behind it that we believe is also super relevant and beneficial to run workloads outside of the browser. So the 4 are, and I've tried to highlight them here, is like you have a very safe model because anything you want to run inside of your browser is being loaded from a remote host. So it is by definition unsecure. So you want to sandbox it, make sure it has its own memory space and cannot move out of that. You want to have these things being portable so you don't have to build like 4 or 5 or 6 or 10 different versions depending on what processing architecture or what operating system needs to eventually run this, because you just want to run it in a browser. You also you want to have these start up really quickly, because typically what we run inside of the browser is something that is graphical UI thing, so there's like human interaction. So you don't want to wait like 10 seconds for a thing to load. You want to see it load quickly. And last but not least, you want to have these things be very small because you're always running these from a remote host. So you have to transfer them over the network before you can actually run them. So if you think about those as design principles behind WebAssembly, and now try to extrapolate those outside of the browser as well, and thinking about what containers really are, there's actually a lot of problems that these design concepts solve compared to containers. So containers not necessarily having memory isolation. I know there are hypervisors that can solve some of that, but by default not. You need to build container images that are natively compiled to the platform where they need to run on. They're not known to be small because of all the file system layers and dependencies that you include in them. And whether they start fast or not, it really depends, but they tend to be a good fit for at least long-running types of operations. And if you have a long-running type of thing, you don't necessarily is concerned so much about startup times. But we'll try to get back to this towards the end of the presentation, and I hope this sort of makes sense in sort of the visionary part of where we believe this whole thing is going. Okay, so I created a very unofficial rough timeline of how these things played out. So a long time ago, this WebAssembly thing was created, right? It's a new compilation target for the browser. It gave us a few things. It gave us this thing called, it gave us WebAssembly, abbreviated to WASM, and it gave us this concept of a WASM module, which was a thing that we could then load from JavaScript within our browser, and then we could run stuff. You've probably seen demos of people who have compiled games like Doom to WebAssembly and running them inside of the browser. So it's one of those examples where you can take other programming languages and get them in there. We're not going to spend a lot of time on this. We'll quickly move on to this time period, which is somewhere in the middle. I mean, we're probably talking 5 years or so, right? But anyways, this is somewhere in the middle. And people sort of realized, well, this is actually useful outside of the browser. There's stuff we can do here. So that gave us another set of W thingies, which is WASI, the WebAssembly system. Let's try again. The WebAssembly system interface. And WASI is really meant to be so when you run WebAssembly inside of the browser, you expect that there's a set of browser APIs that the WebAssembly needs to interact with to sort of interact outside of its sandbox with the outside world. What WASI is a definition of what a system interface, or you could call like an operating system, would look like for these things. So if you take a WebAssembly and you don't run it inside of the browser, so what is the access to the outside world? And that is what WASI is trying to define. So you will see things like file systems, sockets, CLI environments, and those type of things. So that's what we got here, somewhere in the middle, and we're still building WebAssembly modules at this point, which means that we created a thing that could run by WebAssembly runtime. And so where we are today, and sort of where the future is heading towards, is we can actually take these WebAssembly that are already fairly small, but we can even break them down further and make these things composable. And that introduced another set of W thingies, which is called WIT, which is the WebAssembly interface type system. I think it's called type system, I'm actually not sure. But it's an interface definition language that enables us to define how WebAssemblies will communicate, like how they can depend on each other. And this is where we are going to start building components. And one thing that is extremely important for that story is that because WebAssembly is this common compilation target from all the different programming languages, we actually have a system with the WebAssembly component model where we can build a library in one programming language and use it in another programming language, like statically link these things together and run them in a WebAssembly runtime. So we'll try to focus some on the middle and move towards the composition part and how we use these components today. And so let's go ahead with that. So I mentioned WASI, the WebAssembly system interface. So think about WASI as this is what enables us to compile something to WebAssembly and then run it inside of on an operating system or on a WebAssembly runtime. And again, we want to create WebAssemblies that are portable, modular, runtime independent, and have a set of native APIs so that when you build these WebAssemblies and you run them inside of WebAssembly runtime, you have access to things like what's in the bottom here, a CLI environment, standard in, standard out, those type of things, or something like HTTP, a set of very useful use cases where you can either handle just running a run command, or you can handle HTTP requests, for instance. And part of those APIs then have some low-level APIs underneath, which is sockets are defined, I/O, random, clock and file system access as well. So you can think of this as someone is trying to build a operating system for WebAssembly, and there are a certain set of APIs that you can use within that. But that operating system is something that is very small. We can embed it into other programs, and we can move it across operating systems and processing architectures. So what we need to do this is we need that programming language which can compile to WASM WASI, and we need a WASM WASI 020 compliant runtime. And I've gave 2 references here. One is a language guide that we support, so you can sort of get an idea of what languages are supported for WebAssembly and the state of that. And then WASM time is the runtime that we use and is backed by something called the Bytecode Alliance, which is a foundation that creates a lot of work or projects inside of WebAssembly. So what does it actually mean to compile something to WebAssembly? Well, it depends on the programming language. So each individual programming language And their native tool chain really defines these as compilation targets. So if you think of Rust, you will have a cargo build command or cargo component build targeting WASI. If you're in the world of .NET, you have a runtime identifier, which is WASI wasm. And if you're in Go, TinyGo in this case, you also have a target, which is WASI, right? So you take your programming language, and it has some compatibility in order to be able to target WASI specifically, and that's sort of where you start. So let's try this. Let's actually see this in action and build one of these WebAssembly modules. And what we will do is we'll just start by using the WASI API. So this is sort of a recipe of what we're going to do here. You have the runtime down here that exposes these WASI APIs. And we're going to build a module that uses the CLI environment, which means we can run it and we can get standard out from it. And it uses WASI files to eventually read something from a file. So let me check what I have. Actually, let's cargo component. We'll do this in Rust to begin with, just to get started. I'll try to mix in some other programming languages as we go along, at least to, if for anything, just show you how these things work across programming languages. Okay, so cargo new. Hello, CPH. Cargo is Rust's toolchain, so this is what we're going to do here. Whoops, let me get back into my... What happened here? Oh, CPH, there we go. Okay, let me do this again. We're going to build a new one, and I think we should have a directory now. Let's get an edit up and running, and we can see what we have in here. So basically, we are building using cargo command to create a new project. And you can see we have a main function in here, prints hello world. And that's really all we need. There's no dependencies or anything being used. So this is pretty straightforward. And what we can do is we can then use cargo to build this. And now we'll target WASI, which means that we now have a WebAssembly in here. So if we look at what's coming out of this thing, you can see we have a WebAssembly, a WASM file. And what I can do with that, I can then run that with inside runtime, which is my runtime that I'm using for this, and you can see it says hello world. Okay, that's not necessarily very impressive. What's more impressive is that the actual binary that I have, the WebAssembly, I don't need to recompile that if I wanted to run this on Windows, if I wanted to run this on x64, if I wanted to run this on Linux, wherever else I want to run this. It's the same compilation target that I can run anywhere. And you can see I have some of those. I can just run this as a program. What we can also try is we can try to maybe read something from a file system. So let's just put something into a text file, and then we can go back. I need to update that one, but take a look. And I did create a little code snippet over here, so you don't have to see me not do this the right way. Let me just go back, copy this in. And what you'll see now is we can use standard libraries. In this case, we're still in Rust, so we're using the standard library to get into the file system once my message is going to go away. There you go. And we still have a main file, and now we're going to try to, a main function. Now we're going to try to read from hello.txt, and we're going to print the content of that file back. Okay, something that's very interesting, which will happen now when I, let me just go ahead and build this to begin with. Now, things will break as I try to run this. And the reason is that WASI is defined, WASI has defined what is called a capability-based security model, or a security model that is capability-based. What that means is that the sandbox that my WebAssembly runs inside, each of all those APIs that we expose from our runtime, at runtime, we define which of those APIs will be open to the WebAssembly. So if you think about how, from operations trying to run things that comes from the developers, you actually get very granular control in terms of what that individual piece of code is allowed to do or not. So what's happening here is that I can't get to my file system, which is why this one is failing. But if I in wasm time say, well, you can actually get access to the current directory, and that didn't work. I think I might need to do that before. Let me do this. Run, there you go. Now I get access to that directory, and we can read from the file, and we can return that. Okay, so that was sort of like a little bit of the basics of WebAssembly, and you can see how we have this WebAssembly system interface that enables us to interact with CLI, that enables us to do things with files. And again, I've done this in Rust right now. We can do this in other programming languages as well. And I think as we move along, we will see more of that. Okay. So what's also an important, I know this is a little bit small, but I'll try to highlight the most important. But another important point to get across is that WASI 020, again, this is an open standard, right? And a little bit of this goes back to the whole being an answer towards Flash and those type of things. Which means that the same way that HTML and HTTP are open standards, WebAssembly and WASI and those things are also open standards. So when I was using, what I was using before in the WebAssembly runtime is a standard interface that is described and versioned. So I can go to a website called wa.dev, for instance, but other registries as well, and I can find these interface definitions. And part of WASI 020, we talked about CLI and HTTP, has these two very specific use cases where you can see there's either on the CLI side, you can implement a WebAssembly component that exports a run command. Basically in Rust, that would be my main function. In other programming languages, they sort of have other ways of considering. I think in .NET is also called main, right? If you do a CLI program, yeah. So if you are in that interface, you can see that you can implement a run function, and the WebAssembly runtime can run it. But you can also see that you're also able to implement an incoming handler in the HTTP world, which means you can implement a piece of code that takes an HTTP request and returns an HTTP response, which sounds very similar to what you do with things like Lambdas and Azure Functions. But again, this is a standardized way of describing these things, and how you implement the web server and all these other types of things underneath is fully up to you. So you have these standardized set of interfaces out there that are very useful for various use cases. So moving somewhat from the very low-level stuff we've been looking at right now and into something where it's like, but how can I use this today? What's more? What's the opportunity that I have? Like, how can this, how can I have a framework and developer experiences around this? So there is an open source project called Spin, which we created at Fermion, which is the developer tool for building WebAssembly microservices and web application. So really what we've done with Spin is we've taken that concept of the WASI HTTP interface of saying, okay, what if we build, let's just call it a serverless framework. I know there's something called the serverless framework. This is not taken that, but a framework that takes from this developer experience of building things serverless, which means that the only thing that you are responsible for is to implement that particular handler, like the thing that handles the HTTP request. Everything beyond that will take away from you. Or you don't have to care about. We're not going to take it away, but you don't have to care about that. Because we have those interfaces defined, and basically all you have to do is create a WASM module that implements that incoming handler function that the interface specified, and you can run that on top of WASM time. So what Spin really does is it puts a developer experience and some other features around this. There's a whole expansion of this, and we'll get back to that a little bit later. But Spin makes this really easy for you through SDKs we build in various programming languages, but also the developer experience as such. So I think what we can try now is to just use that and try and create one of these HTTP handlers, and we'll sort of start on mind how is this all built and what does the component part of this have to do with it. Okay, so part of Spin is we have a new command, and you can see there's a bunch of templates, and you can see some of the programming languages that are supported. But you can also see there are other things down here like Redis. And basically, you can think of the same way that you can describe an interface where you implement an HTTP handler, you can also describe an interface where you implement something that handles messages from a Redis queue, right? So there's this event-driven notion on the framework, and all of these things are extensible. The only difference is that the Redis pieces are not standardized, the HTTP pieces are standardized, and part of that is really, how fast the ecosystem moves here. Okay, let's try and do something in JavaScript now. So I'll pick a template in Spin to create JavaScript. And if we go in here, we should be able to just do npm install, because now we're in a JavaScript world. So now when we develop, we're obviously in the JavaScript toolchain. So things like npm and being able to import packages through npm is what I do as I develop my JavaScript application. Okay, so let's go back and let's fix the color scheme. There you go. One thing to notice in here is that besides what is part of JavaScript here, which is Webpack and there's package.json, there's some nitwit stuff that we use. I think this is actually something we came up with. But anyways, detail. We have this concept of a spin.toml file in here. And really what a spin.toml file is part of what we created for Spin, because we believe when you want to build these type of applications of WebAssembly, you need an application model. You need a model to describe the intention of these components, and you also need a way to actually build applications consisting of multiple components. And this is something that's an interesting thing you can do when you use WebAssembly based on the small size, the fast startup time, and all of these things. So I can actually create applications that consist of, there are a bunch of HTTP handlers, each listening on different routes, each written in their own programming language. And they can all be the same application. I can deploy them as once, because at runtime, they're just WebAssembly. They're just WebAssembly modules, all of them. We don't know what programming language they came from, but they can all be deployed and work together. And I can even, take dependencies from one component into another, and so on and so forth. So we define components in here. We can see what WebAssembly is going to serve, is the source of that component. And you can see we attach this HTTP trigger saying all routes, this is a wildcard, are being served by the JS Spin component, which is down here. And then there's a bunch of tooling stuff. Again, this is all developer experience things to make things easier. And that's not the one I wanted to show. So in JavaScript, this is what an HTTP handler looks like. I import something from an SDK we built, and I export a function called handler, takes a request, returns a response, and that's five lines of HTTP handler. Universe is probably okay to say hello, universe. So let's go in, and now I'm probably going to get lost in the, but let me see if I can just, we get into this directory that we just created. There obviously has been build command. And now we're going to produce a WebAssembly based on this JavaScript and all the stuff in between. Anybody guess what the command is to run things? That was actually a good one. It's spin up. That's close. Spin it. Spin it would be nice. I think we could probably alias that in the CLI. So there you have it. We now actually, so what Spin does, Spin embeds that runtime, the wasm-time runtime that has all the WASI APIs, which means we have WASI HTTP available. And then we've done a lot of optimizations around loading these modules and taking the app model and providing you to combine things and all of that. So what I'm actually doing right now is not asking for the weather forecast, but I'm just going to curl this JavaScript thing, and you can see response time is really quick. What's interesting is that the model we use is, and you can kind of see it here, is when Spin loads, when we do spin up, we load the wasm-time runtime inside of it. And we load a version of the manifest that tells us which HTTP routes are we serving and which wasm files are going to serve those routes. And then once a request comes in, we're going to load the WebAssembly, hand over the request, handle the request, unload the WebAssembly. So when I do this curl, all of that is actually happening. So there's some pretty amazing performance you can get with these type of things, where these small handlers can be loaded and unloaded very, very quickly. And you can start to get a sense of how, when we think about larger systems or platforms and things like that, where you can put in all these small components that have defined APIs in terms of how they will be triggered, what they can access, and things like that. You have a runtime model where you load them instantaneously when they need to serve something. Like immediately, you don't have to think about scaling the individual workload. You don't have to think about, it enables a lot of stuff in terms of density. You can have much more running on a single server because you don't need to think about when things need to scale up, how long does it take to scale down, because everything is just always available. And that's basically what we've done in some of these implementations of the runtimes. So again, I'm using this as an example of what this WASM thing can do for you. SpinCube is one of those examples. SpinCube is another open source project that enables you to run Spin applications inside of Kubernetes. Both Spin and SpinCube have been submitted for donation to the CNCF, so hopefully they will become sandbox projects soon. But we also built more commercial offerings. We actually built a cloud because we want to show people what the best cloud experience you've ever experienced, what that looks like. And that is the Fermion Cloud. I'm sorry, I know there's a little bit of a pitch, but I'm actually super proud of the stuff we're showing there. We don't make money off of it anyways, so it's not a big thing. But there are these places where you can start running things, and I think we should just try, for the sake of it, to actually do something in Fermion Cloud, just to give an example of what you can do with these type of applications. So, obviously, Spin Deploy takes me into Fermion Cloud. Deploy is a plugin to Spin, so the CLI, you can build types of plugins, so you can build your own Spin Deploy to my cloud or whatever, and build your own cloud, if you so desire. And then we can get our stuff up and running. And what's super interesting about this cloud is that we have a runtime concept. So I mentioned before how each of these WebAssembly components are loaded as requests are coming in, right? So when I run this locally, I have a single WebAssembly, I have a single route that I need to deal with. What we do in this cloud is you can consider on each of the nodes that are up there, the servers. We have one host process. And what that gets is it gets the spin.toml file, the application manifest, for all the applications that have been deployed. And it kind of sort of munches them together into one big index or registry of which host headers and routes do I need to serve and which WebAssembly component is going to serve that. So it really doesn't, this is illustrative. It doesn't be concerned about whether it's your application or my application or whatnot. It's just a host header, it's a path, and it's a WebAssembly I need to run. And because we have that secure isolation of each individual execution being a fresh load, so no memory shared across executions, but also each individual WebAssembly having its own isolated memory it runs in, we can do this in a safe way. Which means that we can have, I think last time we checked, so we did some experiments in AKS and Kubernetes, and we actually ran 3,500 spin apps on a single node. Now, if you compare that to containers where you can run maybe 150, maybe 200, if things are crazy, there's a lot more stuff you can do, right? So that's quite funny. Okay, so we could go over here and we could actually curl our application. That's not going to go well. Anyways, I'm going to do this. That's the application. Hey, there you go. And it instantaneously replies. So again, each of these requests, we're loading the WebAssembly inside of that cloud, and it's just there, and it just responds. So I hope you think that's a little bit amazing. Like that's a nice way of building apps serverlessly. Only think about the handlers and then deploying stuff in there. We have a lot of fun use cases with Spin. We implemented a file server, so if you want to serve static content, you can just, in your Spin application, you just drop the file server in, put your static content, and it now becomes part of your app. So implementing something front-end, API back-end in one application is actually a pretty simple thing to do, and actually quite fun to do with Spin. Okay. Since we are at a is it okay if I call this a .NET biased conference? Yes? Okay. We've actually done a lot of work on .NET very, very recently, and we have a bunch of very experimental stuff where we can both, I know probably a year and a half ago, Microsoft, specifically Steven Sanderson, did some experiments around WASI and .NET. We sort of picked up some of that and moved it towards WASI 02, and are able to build WASI HTTP components in .NET today, and are actually also able to compile ASP.NET Core into WebAssembly. So if you build ASP.NET Core stuff today, you can stay inside of that world of ASP.NET Core, but compile your thing into WebAssembly, and you can move into a hosting model similar to like Spin, or in SpinCube if you run in Kubernetes somewhere. But let's not, so .NET is there. I have a .NET app that's running. I don't know if you actually want to see it, but just trust me. I hope that's okay. But you can see there's a bunch of ASP.NET in here. We've implemented a WASI HTTP server, so that all works. I think the main thing is, I'm just going to close that. You can see we implement all of these ASP.NET Core stuff. So in the handle, you can start creating a Slim builder. Add your logging and add all of these other things that you want, static files, put your routes in and all of that. So this should look fairly familiar, .NET code, if you're in the ASP.NET Core world. And again, this compiles down to WebAssembly, and you can run that today. There's actually one thing that I wanted to show over here, because what we created in here is a WebAssembly file, right? This is JavaScript compiled to WebAssembly. You might think that this is a little bit on the larger side of things, but JavaScript is a little bit of a tricky thing in WebAssembly, and that is a scripting language, so interpreted at runtime, which means that part of how we build JavaScript today involves some of the interpreter in there. So JavaScript files in WebAssembly tend to be large. Rust files in WebAssembly tend to be super, super small. There's also a lot of debug info and stuff in there that we can strip away, but there really is a correlation between what programming language you use and how small these WebAssembly end up being. But the point that I wanted to get to actually is that even though that we used Spin to build this thing, and we saw that it ran in Spin, because this WebAssembly uses WASI HTTP, and we can actually go and inspect the interfaces, if I can remember the right command. Is that with? Oh, component with. There you go. Okay. WASM tools, component with. By the way, you probably get the sense throughout this that we are at an early maturity state. There's like 25 different tools that we use, and I can't remember half of the commands and all of that, but I mean, it's all fine, we're getting there. But what we can actually do is we can go ahead and inspect this thing, and what we can see in here is you can actually see the with definition, that WebAssembly interface type language, defining what is this component doing? Like, what does it need and what does it give us? And what we can see is that, let me get over here. What we can see here is that there's a bunch of interfaces that we import. So now we're the handler, right? We're the handler. So we expect someone to provide us with all those interfaces, and then we will give back an incoming handler. And if we looked at the, which means that our runtime will sort of have the opposite, right? It will export all of the above interfaces, and it will look for someone who imports the, and it will look for someone who exports the income handler by importing it. So what that means is, because Spin has built a standardized, compliant WASI HTTP component, we can actually run this in WASM time. So we could do runtime 1, and I think we need to pass in a weird argument as well here. And we should be able to, no. Ooh, why can't I do this with this guy? What did we do the last time? Do I need to do a component run? Was it small s? Oh, sorry. There you go. It's wasm time serve. We want wasm time to be our HTTP server now, so that's why it's serve. And go back, and we can see the same JavaScript thing that we built before is now going to be served by wasm time. So if it has to be a different port, we can still do hello universe. Okay? So again, component, different runtime implementations, as long as these interfaces are all there, this is stuff we can do. Cool. Okay, so let's try and get to how we can use that component model in practice, because really what we've been doing so far is just working with that standardized interface WASI. And what we are getting at this point is, well, let's see, it's not only have a runtime and build this one module that uses the WASI interfaces, but how if we want to have the thing that we provide being composed of multiple things that came from multiple programming languages. Can we do that? Yes, we can. So there are some high-level goals defined for this component model. Again, portable, low runtime efficient, so small, quick startup time. Separately compiled, meaning I can take something written in JavaScript, something written in Rust, and then we can bundle them together and we can do cross-language composition. And you could ask, who asked for cross-language composition? I don't think anyone necessarily asked for it as such. But if you think about what we have done with Spin as a framework, the ability to have a single runtime implementation that supports you to bring HTTP handlers in any programming language you desire for whatever reason is a place where, you know, well, that cross-language composition thing is actually, it does actually make sense. Our CEO wrote a blog where he was like, well, what if we only have to support one Postgres driver in the future, and it was written in the most optimal language to write a Postgres driver in, and every programming language now only use that one Postgres driver, and we don't have to support and maintain hundreds of different Postgres drivers across programming languages. That is definitely a vision. I know at NDC Oslo, what's his name? Dylan Beatty talked about it. He had a talk about open source and package managers and had this idea of WASI becoming the package manager to rule all package managers eventually. Yes, that is theoretically possible. Whether that will ever happen, I don't know, but those are the type of things we can actually do. So what is inside of this? Well, we have a rich type system, first of all, which means that we can define these interfaces with a bunch of types. Actually, I think the WebAssembly specification only works with 4 data types. And what the WebAssembly component model then enables us is to have a much more wider set of data types that we can work with. So when we define these interfaces, we have more options. We have the interface type language with, and we can define these contractors interfaces. And actually what we do is when we bundle interfaces, we call them worlds, which is quite, I like it. I think it's quite cute because you can talk about that your WebAssembly lives in a given world, which means I live in a world that gives me these APIs where I provide this API. So if you are a runtime or a platform or whatever you are, you can say, come to my world, and your world is actually defined as a set of interfaces, which is quite nerdy. But anyways, okay, we can go off of that thread if you want. Maybe later, maybe over beer sometime, but yeah. But anyways, end result is we can do these compose applications functionality across programming languages. Okay, let's try and do this in practice. I tried to create another sort of stack diagram or whatever we call this with some pseudocode. I don't even know what syntax or language is, but I immediately see there's an error in the print statement. But anyways, but again, we have the WASM runtime at the bottom. We have the WASI API, the WASI standard API where we use WASI CLI, so we call run and we expect to get something back on standard out. The first component basically implements the code saying print hello, and then I'm going to get the current city from somewhere. Now we're going to take that component and we are going to describe an interface so someone can implement a component that gives us the current city by implementing a current city function that returns a string. Bear over with me, we're trying to just do the example that, and then we can think about what that might means. So I think what we're going to do here is I'm actually just going to browse to the Finnish code instead of building this from ground up because it'll just be too much of me standing here and copy and pasting thingies. So, okay. Let's first look at the one the component we have at the bottom. I'm going to call this hello. So this one has this with definition. The package name is just, eventually being used so we can host these things in registries, meaning that we don't have to have our interface definition locally, but we can basically say, this package with this name in this version is what I'm targeting when I'm building my thing. And these things can then live in registries, like from containers and package managers and so on and so forth. But the thing that I'm building right now targets this world called Hello City. And I will be importing from a package called component cities the interface called city info. So what I have in here, again, this is written in Rust, two things. I have my toolchain providing bindings for me, which means that my toolchain understands how to translate this with definition into some Rust code that I can then write against. Okay, so that's all generated code. Depending on the programming language you're in, there are various binding tools to use. I'm going to show a .NET implementation of this as well, but we'll just start out with Rust here. So basically what Rust's we need to do is we can import those bindings, we can import those city info, the current city function is defined within there, and then we can implement a main function, said, let's go and find a function called current city, and let's print hello current city once we get something back. But there's nothing in here that implements the function of a current city. Where that is implemented is in this other Rust implementation up here. So basically, the link between the two, and again, this is dependent on the toolchain, is in cargo I can actually say that component cities package that I was referencing in my with file, you can go and find that here. So this is a path, but this could also be a registry reference. So I could I could publish this with definition somewhere in the internet and just reference that here. So I actually now have a dependency on this package. And what that package looks like is this. There is an interface called city info. City info has a function called current city that returns a string, and there's a world where we export that interface city info. So what I'm doing up here is I am implementing cities info. So I am implementing the function called current city that returns a string, and we are in Copenhagen, so let that be Copenhagen. And we will export this, so we know that we have a component now that will be exporting that particular interface, and we should be able to try and run this. So let's go over here and in our backup folder. Let's start by going into the hello, and what we will do then is we will start building each of these. So first we will build the hello thingy, and then we will build the city thingy, and then we can go back. See, did I put things? I'm just going to go in here because I might have. We will then use a tool called WASM tools, and we can compose these things together. So basically we are saying take the hello WASM, take the, not the .NET one, we'll get back to that later. WASM tools, compose, and this is the one. So take the hello WASM, take the cities WASM that implements the get city function that we need, and output a WASM file called composed WASM. And once we do that, we are not. Let's see, where are we? Target, debug, up. WASI, debug. Something, this file is not aware. Oh. Okay, let's go back. So cargo component build, there you go. We are actually going to build components now. We're not going to build modules. So let me go back and fix that. So now we actually have real WebAssembly components, and we should be able to compose these together. Yes, and we have a composed WASM. And again, we can use WASM time because we're just doing CLI, and you have hello Copenhagen. So we have one WebAssembly now that we created from those two. Yeah, you can, yeah. Woo. Thank you. But we can also do that in .NET. And this is so experimental that I actually have to run a Windows machine in Azure to even build this thing. So if you want to try this at home, Just make sure you have like at least a whole weekend to get this work. No, it's not that bad. But anyways, if you wanna, can I zoom here? I can zoom. This is the secret thing to try and build WebAssembly components in .NET. So inside of Bytecode Alliance, there's a repo called componentize.net. They all call componentize, componentize.net, componentize Python, componentize JavaScript, yada yada. But componentize.net actually has a really nice walkthrough of how to do this. But really what I wanted you to show, if you're more familiar with .NET, is how this is going to look like. You have the width definition on the right-hand side, and you have the code that I need to write on the left-hand side, which basically, I'm in that namespace, the cities world with exports component cities thingy, and I am creating information of the iCityInfo interface, which you can see over here. And there I'm implementing that function called current city, returning Copenhagen Developers Festival. So we should be able to .NET publish this. .NET 8, .NET 9 would work. .NET 9, I guess, works better right now. And by the way, if you feel into this and you are very savvy .NET developer, anyways, if you feel into this and you like .NET and you like to write C#, there's a good opportunity to impact this whole experience. Like, how does the code on the left-hand side, how should that actually look like? What feels most natural as a C# development in terms of implementing these type of interfaces and so on and so forth. Because there's a lot of stuff going on behind the scenes to generate the bindings and all these things based on the WIT file, and all of that is really something that people have to invent. I think you can even see how the binding, the interface definitions and those type of things are generated. Like, this is all code generated by this NuGet package. So how these things make sense and so on and so forth, again, this is very language specific, but there's definitely opportunity to impact some of that. Okay, we did build a component. I'm gonna try and copy this out of my VM and over here. And I am gonna replace. And now we should be able to compose our hello thingy, the thing that says hello and asks for the current city, with our .NET component. And let's just get composed. And now we have a local Copenhagen Developers Festival. And someone added a to-do. Somewhere in the tool chain, there's a to-do being written out. I have no idea where that actually comes from. But what we basically did is we took a function written in Rust, some Rust code we compiled down to WebAssembly. We took another function or an interface implementation written in .NET, well, written in C#, compiled to .NET. I guess that's the right term. But anyways, and then we took those two WebAssembly and we composed them together into one WebAssembly binary, and we could just run that because they all conform to the CLI thingy. So I hope that sort of gives you this idea of where this component model adds to this whole thing of having small, portable, fast, runnable thingies that we can then, compose together in these various scenarios. And really, we've done a lot of this. We used all of this inside of Spin. So Spin is not only a thing that can do WASI, HTTP, and Redis, but it also have a bunch of ways of interacting with things outside. So, having to store data in a key value store is something that's super easy, using LLMs like inferencing. So this would be the marketing representation of Spin is. This is the WIT representation of what Spin is. So you can see we have these worlds defined in here. So basically you can see if you wrote a Spin app targeting the world platform, you get access to configuration, you get access to outgoing HTTP, you get access to Postgres databases. There's a MySQL interface, SQLite interface, Redis, key value, LLM. What's even more interesting in the way that these things run inside of Spin is that if you use the key value interface, which is like, KV open, KV set, KV get, and so on and so forth, pretty straightforward. Because we have this model of plugging things together, we can actually, inside of the wasm time embedding that we do, so the Spin process, we can have the key value store being backed by any different type of database technology you want. And this is actually super interesting because it makes for a really awesome developer experience. So I spent a few years in the Azure DevTools team in Microsoft building some of those developer tools for Azure. And one of the things we constantly had to deal with was, how do I get a blob storage on my developer machine? I guess some of you kind of been there. Like, there are emulators and other types of things. I think there are even some open source efforts in terms of doing those type of things today. With a model like this, it's so much easier. So the way that we've implemented key value store for Spin locally, we just use a SQLite file, and we just have a table structure in there. And once you move them into Fermion Cloud, they actually are stored into a cloud provider's managed database offering. If you run inside of Kubernetes, you can provide a runtime configuration file saying, this is the Redis file I want to have backed. So when you think about how things move from development and using standardized APIs into a platform, the platform gets to define what is the implementation of a key value store here, but also what is the implementation of all these other APIs that are available in that world. So I think that is super interesting and super inspiring around this component world. And I don't have time to do this demo, but basically the idea was just, I built my own host, and that host can dynamically load WebAssembly components. So I have this thing where I can put in a string, and I can start adding more components in, and the more components I add in, the more transformations I can do with the string. So basically, turn them uppercase, reverse them, obfuscate them, whatever I want to do. So if you embed a WebAssembly runtime in your own host, you can do fun things like that. That is part of this dynamically loading things. To leave a little room for Q&A, I am gonna maybe skip some of this. Well, let's do a little bit of the the visionary type of the presentation. So, some of the people we have worked with around sort of figuring out what is the right developer model for Spin, what's the developer experience you want to provide, and how can we use all of this technology to think about, I hate calling it developer productivity, but I guess you know what I mean, right? Like, to make things easier, right? To not have to deal with waiting a long time to go through, building, debugging, going back and changing code, and all those type of cycles. Making sure it works on my machine, also works once it gets into production. Like, all of those type of things, right? All of those irritating things where small configurations and things are in the way of just like moving along. There's definitely a way to think about how these components can stack on top of each other, sort of like in an onion shape. I have had people, and I think part of that is also, enabling how we can put guardrails around the type of code that we write, not only from the security model of things being sandboxed, but also, give people very specific interfaces that might even be fairly close to, the business context they're in. One example is, with Spin, we ask people to implement HTTP handlers. It's like, why does every single developer who needs to build some kind of businessy type of workflow have to deal with HTTP even? So I have a sample of that. I'll try to share some of these samples afterwards. But we have a sample where actually you could define an interface in between the HTTP handler and your business logic that is, I will give you JSON. I know JSON is not it might be an okay sample, but you could also strongly type it. Like, you could define in WIT what the actual data structure is that you will hand over to someone, and they will deliver you a strongly typed data structure back. And that's all they had to do. And you wrap that in an HTTP handler, or you wrap it in a CLI run, or you wrap it in a Redis trigger. Like, all the means of transportation of getting the data that they need to manipulate or do something with and returning it back could be wrapped in whatever transport you want to define, but then in a strongly typed interface towards that. And I tend to think of this as, being able to build these comprehensive compute platforms, where, today the interface between development and platform engineering or development and operations, tends to be a container runtime, right? Most people work in an environment where they can run a container, or they have some other well-defined interface. But it is also a very common interface. Like, it doesn't have necessarily a lot of things beyond that. So this idea with these comprehensive compute platform, we're really trying to think about what can I, in the context that my company works in, how can I make my platform more specific to the context we're in, and take away a lot of these concerns about HTTP and maybe even authentication and other types of things, and just have people add in, which I guess is like a lot of use cases. Get some data, check some stuff in external systems, manipulate the data, and return something. And you can actually do that with this type of model. And you can think about how, I mentioned key value as a component. Like, you get a key value store, you don't know where it's stored, you don't know how that implementation of where it's stored works, but you get access to it. I have an example of data obfuscation where basically you have someone who writes against a WASI interface to get the data out of a SQL database, but then you can inject a component in between that both imports and exports the same interface, and then you can start doing things with the SQL queries. Like, for instance, you could obfuscate PII data coming back from the database and things like that, which I guess is another example of how you can compose data security into your applications. So, key takeaway, I believe, from the component stuff is, you have self-contained units of work, they allow interaction across programming languages. We have rich contracts. We can build platforms where things are being loaded dynamically, and we can compose systems for components. And then I have the big polyglot dynamic platforms. Doesn't that sound very futuristic-ish? Whatever. Think about it that way, right? You can support things that are much more dynamic. You can build platforms that are much closer to the concerns of what people are actually doing. And you can enable all of this in a polyglot way, and the world will be a better place. Thank you. I put some search terms in. I didn't want to put links in because that's really hard, but good search terms. Feel free to reach out afterwards. I'll stick around. Fermion has a Discord server where we discuss a lot of the open source projects and anything WebAssembly. So also feel free to come there and hang out. We do have a few minutes left for Q&A. There's a microphone down here. If you want to go there and ask a question, we can do that. I'm also happy to take questions afterwards. Thank you. Yes. Do you mind go to microphone? There is a stream going on as well. So.
I just want to ask, what is your thought on the debugging experience? Because when you cross the language, right, and it becomes a challenge. So what is your thought behind that?
It's very poor. There's no breakpoint debugging support in any of the language toolchains today. I know. Actually, Microsoft did some work to enable WASI support for extensions in VS Code, and they are trying to break some waves there. So it is again. So I think this is one of the Achilles heels of WebAssembly. Like the thing that's very hard, to fix is that there's a lot of problems that needs to be solved in each and every language toolchain, and for instance, breakpoint debugging would be one of those. There are GPD debugging you can attach to WebAssembly component, but then you will sort of get the bytecode out. You won't get the stuff out in the program language you originally wrote it in, right? Which doesn't feel very. So yeah. So if you like to work on debugging, then come to the WebAssembly space.
Hello.
Hello.
So for the components, a lot of them package like the Python runtime in itself. How do you see, like, in a system with a lot of components, won't the runtime be packaged like 50 times for each component and have to start up and boot up and stuff like that?
So the model that Spin uses, the runtime only runs once. There's just one implementation of the runtime. So the runtime dynamically loads each and every component.
Oh. Yeah, not the WebAssembly runtime, like the Python interpreter. Is
the
runtime, the .NET runtime, the things that run the the code you compiled in. Yeah.
Yes. At least for the scripted languages like Python and JavaScript, there is work to be done to get those sizes down, and those are things we are working on. I think we are quite okay with .NET. I saw the ASP.NET Core thing that we can build today. You can actually get something up and running that was around 17 megabytes. That's an ASP.NET Core application, whereas one of my Microsoft friends told me that the smallest ASP.NET Core container is 60 megabytes. So, I mean, there are those comparisons still. Like, it would be super nice if everything was like, 17 kilobytes like Rust, but that's not the case for all the programming languages. So there are still those trade-offs. Yeah. Thumbs up. We're done. Thanks everyone for coming. I'll stick around for questions and conversations afterwards.